So we were able to calculate the volume of flow rate. The master equation is the density mass over volume, and then if you're gonna manipulate that, volume is mass over density. So we have this mass. We're able to compute the mass of air, right? The mass of air, and then this is the density of air is pretty much standard. So the mass of air we're able to compute with these calculations below here, right? Mm. So here, if in order to get the volume, you should get the mass of air, no? And this also MCP, no? Q equals MCP delta T, no? So Q of air, no? Q of air equals MCP delta T. So what we need to have is the M. So we have the delta T, that is negative zero point 0.7 times negative 2 at the evaporator side, and the CFP of air is pretty much standard. It is um, 1.006 or 1.01, if you want to round it up. So and then Q air is 277 kilowatts. That's the amount of load in the chilling room, including the lights and the fans and the heat gain, no, plus the cooling load of the product, which is the beef, which is 235. So we're gonna have a 102 kilogram per second, and that's the mass, right? And that's the mass of the air. So what we're going to do with that is we have a mass of air, then we have density of air, which is pretty much standard, 1.293 kilogram per meter cube. So kilogram and kilogram will be canceled. So the volume is 78.9 meter cube per second. So the next question is, what is the volume of air in the chilling room? 78.9. Now we're good at that. In that, what is the product refrigeration load? 235, because that is for the product only, which is the carcass. Then if you're gonna add the fans and the lights and the heating gains, the surroundings, it's gonna be 277. No, that's the refrigeration load, and this is the product load. No, product refrigeration load. Only the product, not the others. So if you're gonna have some dishes or others load, it is not included. Only the beef, no, or the carcass. What is the heat transfer surface area evaporator on the air inside, assuming all the vapor and the fog in the air freezes in the evaporator? So we're gonna have a 2,764 is square meter. And how did we just get that 2,764 square meter? This one, no? So there's a formula which is Q UA delta T in the convection side. No? So convection Q equals UA delta T. So U is the overall heat transfer coefficient in terms of convection. A is the area, and then delta T is the change in temperature, right? So if we're gonna have that, we can solve for this, which is uh, the overall heat transfer is 20 watts per square meter Kelvin, and the delta T is 5.5. How did we get that 5.5 delta T in the evaporator? So if we're gonna look back at the evaporator, there was a given here about yeah, here, yeah. Also the average temperature difference between the air and the refrigerant. The air outside and the refrigerant inside the tube of the evaporator is 5.5. That's why we have this 5.5 here, right? Delta T. Then 20 is the overall heat transfer coefficient, and here is the evaporator load, no? Evaporator load, because you're gonna get also those some moistures or the droplets, right? So that you can use also as energy. So we'll finish with that. Then for COP, what is the COP? That is a refrigeration effect over work of compression. So the question here is for the COP is this: what is the total heat removal at the evaporator or total refrigerating effect? So if you're going to get the refrigerating effect, that is the total heat that is removed, no? So you're gonna have that here, no? Total if refrigerating effect was computed with this, right? That's mh, right? So Q freezing is right 0.08 kilogram per second. That is our the flow rate, and then we have this flow rate which is zero point zero 0.08 kilogram per second times 333, or the latent heat of fusion, let us say 333 or 335, we're going to end up in 27 kilowatts. And then Q evaporator is the Q cooling load plus freezing. So you get the cooling load, which is 277 from different sources like the fans and the heat gain and the lightings plus 27, which is this some amount of water, and then they are dripping. They have to be kind of cooled now, zero point zero 0.08 kilogram per second divided by 333.7 kilojoule per kilogram. So that's gonna be the answer, 304 kilos. That's the evap. And but here the area is 2,764 square meter heat. Now that is the the formula for heat, charge or heat. So we're gonna have the COP, that is the heat refrigeration effect over work of compression. So the refrigeration effect is what? 304 kilowatts. That's the load at the evaporator. All the heat that the evaporator should carry, should absorb into the refrigerant. So that's gonna be accounted for, and that is 304. Now kilowatts over the what is this? Work of compression. That's 7.6 kilowatts, no? Or 76 kilowatts, as can be seen in the problem. The power to the compressor is rated at 76 kilowatts. Where's that? Yeah, here. That's the compressor input power. That's why you were able to calculate the center the coefficient of performance, which is 4, which is pretty good. Yeah, from 2 to 3.5 is good. No, 4 is very good. So 3.4 is 3.4. 4 is the coefficient of performance when you divide the 304 kilowatts of the evaporator, plus the, of course, it includes the cooling load, 277, plus freezing, which is the coming from the waters and the moistures going to the top of the evaporator cold. So they put that as 27. So okay, so we will have that 304 kilowatts. So the other thing is the coefficient of performance when you get the 304 kilowatts. 4 kilowatts is the capacity in the evaporator. You just have to divide that with the total power, which is 70 kilowatts in the compressor side or compression. So now the arithmetic temperature difference is this, right? Arithmetic temperature difference this negative zero point 0.7 tapos may zero point 0.4. Then this one is minus 2 minus 4. So there's a formula na here, no? Negative zero point 0.7 minus zero point 0.4. There's a negative 2 and negative 4 for the temperature difference. So the temperature difference is 3 point some. So the temperature difference is 4 point, no? 4.7 when you calculate this, no? So this is another calculation, QUA delta T. So we just have the value because the K is there, and it's like U is the resistance of uh, X is there and K. So 1 over R, there's a invert relation with respect to R and K. So U is 1 over R, then 3 inches over 20 is 15. So U is 1 over 15 now, because there's a inverse relation with respect to U and uh, okay, U and the resistance, right? U 1 over R. So here there's a inverse relation. Okay, so now we're gonna have this the Q in another problem. So we go back to the problem so that we can finish the problem about the carcass. So we're gonna continue with this total rate of the heat removal at the evaporator, total refrigeration effect. It's gonna be 304 kilowatts. So we're able to to solve that with this 2 weeks extra, no, the I mean the extra for the cooling load, no. So this one is right here, yeah. So we have this 300 kilowatt. Okay, so we were able to answer all this, right? What is the mass flow rate of air? It's going to be 102. What is the total rate heat removal at the evaporator alone? At the evaporator alone, you have a 304 kilowatts because the other moistures and the other wet coming in is converted all in all to cooling air, right? So there is this, and then what's the amount of mass needs to be cooled per unit time, no? So we have this 3.56 kilogram per second as what we uh, used, yeah. So also this uh, evaporator total heat rate is the same, 4 kilowatts. And what's the mass flow rate? We already computed 102, no, because we were able to compute the mass flow rate also. And so mass flow rate and we continue with the questions, of course. So here we are in this question about COP. It's already answered. It's 4. Why? Because the output, no, is the capacity performance is the overwork of compression of the refrigerating effect, and that's what we were able to have this 304. What is the mass flow rate? So this is 102. And then what is the arithmetic temperature difference? So this is 4.7 according to calculations. And what's the mass flow rate? 102 kilogram per second. Now there's a problem here. A cooler, 10 feet by 18 feet installed with the equivalent 3 inches of extruded polystyrene. Proportional gain is 0.2 BTU per inch per hour square feet degree Fahrenheit. And then these are the choices. So it says 11,867 BTU. So here, as a rule of thumb, what is the ratio of the volume flow rate of air to the ton of cooling for a normal comfort application? So we're talking about the volume of air. If you have a 400 cubic feet per minute per ton, that's going to be the refrigeration, no? Ton of refrigeration. No? So here, which is the cross section for ducting? Of course, so that's it, right? So that is 400 cubic feet per minute of air per ton, right? Because there's a rule of thumb of 400 per cubic feet meter cubic feet per minute per ton. So what is the equivalent ton of refrigeration cooling at 3006 cubic feet per minute? Uh, so we're here, right? So 400 cubic feet per minute per ton. And if you're going to calculate this, 7 ton, no? Which is better cross sectional for ducting given the same area. So same area, so it's better for air conditioned room. Yeah. So better a cross section during given the same area. So circular is better. Which is of the two will most incur like dynamic loss for pressure and ahead when used inducting. So long radius term curved circular bed. So when it's long and it's circular, then the lesser the pressure drop. No, when it comes to stricter uh, demand, stricter regulations. So here, which of the two will most likely incur less dynamic loss for pressure and head when used in ducting? So less dynamic force or less dynamic loss. So the less dynamic loss is long radius circular beds, like we have already taken up, and then a flooded chillers operating with a refrigerant temperature. The chilled So here the answer is 15.61 because we're able to calculate the LMTD. No, and then again, which one of will most likely incur less dynamic loss for pressure and head when used in ductings? The long circular radius. And then here, what's the input power to the compressor? We already have this 1.7 kilowatts. We're able to compute that. Which of the following major components that in the vapor compression are responsible for producing cooling effect? Of course, the evaporator. Which among the following process improve refrigeration effect? Of course, that is subcooling. So it's more in subcooling because it try to expand the area for the initial and for the other requirements. So subcooling, the area would increase in the evaporator side, and then the area is increased, then the refrigeration load will be more efficient. So increasing the or extending to the use of subcooling will increase the the the, the criteria for that or the answer. Yeah. So meaning the refrigeration effect will increase if you make the subcooling area now towards the left of the page diagram a bit larger. Now, so here are all the calculations, yeah, for surface area. We already have done for chapter uh, this the about UA delta T, the expansion of the uh, area also, and then this one BTU solution to 11 is the reciprocal between K and R. Now, so K is reciprocal to R or R is reciprocal to A, right? So this one is about a problem, no? LMTD. So here we just have to get the formula for Q is M delta H. We're given two enthalpy, and then we will have to combine the enthalpy so that we can have the total, no? When we multiply the mass. So H2 minus H1 minus the total enthalpy for the gas. So meaning the gas and the enthalpy now should be calculated or multiplied so that we can see the really the water part of here. Okay. So here is the 1.7 kilos. So pretty much that's the answer for the ABCD, right? Okay, so I think that's it for the HVAC side of the mechanical engineering law. So we'll continue with the pump side or the fluid machineries.